So now let's talk about the somatic sensory system. This is another example of one of the mechanical sensory systems because it involves detection of mostly mechanical stimuli, meaning physical pressure against the skin. So there are basically four types of things that the somatic sensory systems detect. The one that you're probably most familiar with is touch. So touch is just physical contact or physical pressure against the skin, and then pain is also part of the somatic sensory system. So the receptors that detect touch, some of them also are pain receptors and temperature receptors, and by temperature here we mostly mean skin temperature, as opposed to internal body temperature. That's detected by a separate part of your brain, which is not really one of the sensory systems. And then proprioception, again, we talked about that a little bit in the last chapter. That's the sense of where your body is in space, and so we'll talk about that one later when we get to the motor systems. But really, when we talk about the somatic sensory systems, the word somatic just means body. So for the most part, it refers to those sensory systems that are from receptors that are in your body, meaning not in your head. So everything else we've talked about up until now, like sight and sound and taste, for example, are all involve receptors that are somewhere in the head or the face. But this chapter deals with all those things that are essentially from the neck down. So the skin is the largest organ in your body, and it is the main sensory receptor surface for the somatosensory system. Skin, as you probably know, is mostly is there to keep the inside of your body separate from the outside. It's mostly made of, the part you can see is this outer layer called the epidermis, which is mostly made of just dead skin cells. Those skin cells grow out of a layer of cells that are constantly being replenished. So you're constantly growing and replacing your epidermis. And there's two kinds of epidermis. The glabrous skin is skin that does not have, usually a little bit thicker and softer, and does not have hair, whereas hairy skin, as it implies, has these little pits called hair follicles. We'll talk about them in a minute. So, and of course, this is just for mammals. Other non-mammals would not have hairy skin, but have scales usually, and so their skin looks a little bit different, but basically serves the same function. The skin is waterproof, and for the most part, things cannot get in or out through your skin. But like I said, the skin cells are replaced constantly. In fact, the dead skin cells are constantly sloughed off and just sort of make their way into the air. In fact, if you go around your house or your bedroom and you see a layer of dust on something, most of that dust is actually dead skin cells, because that's what happens to those cells. They just float off into the air, and then they eventually settle somewhere else. And so that's usually what you're cleaning up when you've got you're cleaning dust off of something. So below the skin, or below the epidermis anyway, you go into the dermis, and so that's the thicker layer that's underneath the epidermis. That's where the blood vessels and other living parts of the skin are found. So below the epidermis you have epithelial tissue. There's a layer of fat that's right underneath the skin. Mostly that's there for insulation. It helps keep the temperature inside your body warmer than the outside, or retains heat inside the body anyway. And of course, it's also there for energy reserves and cushioning and other jobs. But the sensory part of the skin are these sensory receptors called mechanoreceptors. And they're called mechanoreceptors because they detect mechanical stimulus. So that just means any sort of pressure or deflection of the skin will activate these receptors. And they're activated by mechanically gated ion channels. So we talked about mechanically gated ion channels in the context of the auditory system. And so here we've got mechanically gated ion channels that are just found in the ends of these axons. So that's all these mechanoreceptors are. They're just axons that come from cells that are, their cell bodies are way back close to the spinal cord. We'll talk about them later. But in these axons, there are ion channels that open if the axon gets stretched or twisted or bent or squeezed or in any other way mechanically distorted. And when they open, they let sodium in, and that creates a depolarization, and that then can trigger an action potential, and that action potential travels back to the spinal cord. One of the differences between the somatosensory system and the other sensory systems that we've talked about is that these receptors themselves are just axons that come from the spinal cord, and they are not. They don't have specialized cells at the end that are there to transduce the stimulus. So when we talked about the visual system, for example, the retina has special photoreceptors in the retina that detect light, and then those synapses or connect to the neurons that are going to communicate with the brain. And same way with the auditory system in the cochlea. You have hair cells, they actually detect sound, and then they synapse with cells that communicate back with the brain. But in the skin, there are no sensory cells in the skin. The sensory receptors are just the peripheral ends of these long axons that go all the way back to the spinal cord. And the axons themselves are the receptors. And there's different types that have different properties depending on how deep they are and the kinds of endings they have. So some of them, like these guys, Merkel's discs, have a specially shaped ending that allows them to be positioned right here between the dermis and epidermal borders. So right here at the surface of the skin. So they're very shallow. And then some axons have no specialized ending at all. So this axon right here, it just branches and terminates in the skin. And some of these endings are close to the surface, some might be deeper. And in fact, these free nerve endings are found all over your body, not just in your skin. And these actually are responsible for detecting pain for the most part. So we'll come back to those later. Another specialized structure that's close to the surface are these Meissner's corpuscles. So a corpuscle is just a little structure that in this case is kind of surrounding the ends of these axons. And so these Meissner's corpuscles are close to the surface. The corpuscle kind of changes the physical properties of the nerve ending. So it affects the type of sensation that they detect. And we'll talk about that in a little bit. And then hair follicles also have somatosensory receptors associated with them. They're called hair follicle receptors. And they're pretty simple. The axons just wrap around the base of the hair follicle. So hair, you probably know, grows out of these little pits. The hair follicle is the pit. The hair itself doesn't have any sensory receptors. The hair is just made of dead cells for the most part. But around the hair follicle, there are little sensory receptors. Now, for humans, that hair is not an important sensory structure, but you probably know that your hairs are sensitive. So if something brushes past a hair on your arm, for example, you'll feel it even if it doesn't touch your skin. Air blowing across your skin can make the hairs bend. And then, but then for other animals, like say rodents, they have specialized hairs that are really dedicated to sensory reception. So whiskers are a good example of that. Animals like cats and rats that have whiskers, their hair follicle receptors are very, very sensitive, and actually a big chunk of the brain is devoted to processing sensory information from those whiskers because they use those especially for navigating around in the dark. The hair follicles' other job, of course, is to provide insulation, and then to also, in some animals, to act sort of as a communication device. So, for example, there are, you can't see it in this picture, but there are little muscles attached to these hair follicles that, when they contract, make the hairs stand up straighter. Those muscles are activated by various parts of the nervous system, including the autonomic nervous system. which we'll talk about later on. And so they can be activated when you under situations of fear or stress. And they can also be activated at lower temperatures, because raising the hairs up, making them stand up, improves the insulation of the hairs. And that is not so much an issue for us as humans, because we've lost a lot of our body hair. That's one of the many things that makes humans unusual. We have less body hair than most other mammals, but we still have those little muscles, and they're still activated by the same thing. So when those little muscles activate, the skin around the hair follicle kind of bunches up because the muscles are contracting. The hairs do actually stand on end, and that sensation of having your hair follicles do that, sometimes it's called goosebumps. So you have goosebumps sometimes when you get cold or when you get scared or anxious, and that's again because those hair follicle muscles are activated by the autonomic nervous system. But as a sensory receptor, it's just this axon that wraps around the hair follicle that allows you to detect the movement of hairs. And then deeper down in the skin, you have two kinds of kind of deep receptors. The Pacinian corpuscles look like this, so they have just a single ending that's surrounded by this big kind of onion-like corpuscle. And then a Ruffini's ending, which is also deep, but has an ending that terminates in lots of little branches that are also surrounded by this big loose corpuscle. So again, all of these different types of receptors have different properties because of the structure of their endings. And so each receptor, in addition to having different positions in the skin, different depths, have different receptive fields. A receptive field is something we've talked about before, and so every sensory system, or every part of a sensory system, has a receptive field. It just refers to the area of the sensory surface that a given neuron is activated by. So for mechanoreceptors, the receptive fields are pretty straightforward. For any given receptor, the receptive field refers to the patch of skin that neuron is sensitive to, and it's pretty easy to find the receptive field for a given neuron. So if you can record stick a recording electrode against a nerve or against an axon, simply touching the skin can show you where the receptive field is for that axon. So that's what they're doing here. They've got an electrode next to this nerve, which contains axons that come from the skin, and a stimulus probe is used just to press against the skin and find which parts of the skin that cell responds to. So if you press this part of the skin and this neuron fires action potentials, or there's action potentials recorded, that means that this area of the skin is the receptive field for that axon. And you can show that different types of receptors have different types of receptive fields. So some have very small receptive fields, like the Meissner's corpuscle. So these little blue areas are the receptive fields for Meissner's corpuscles in the hand. Each little blue oval or dot is a region that's detected by a different corpuscle. So they're relatively small, they're kind of spread out, and then meanwhile Pacinian corpuscles, for example, have much larger receptive fields. So for example, this whole area here, this whole side of the hand, is the receptive field for one Pacinian corpuscle. Same thing here. The middle finger here, the palmar surface of the middle finger anyway, is the receptive field for just one Pacinian corpuscle. What that means is that for this particular cell, whatever cell they recorded from to detect these fields, they can't discriminate between a contact point at two different places within this area. So this receptive field, if you were to touch this part of the skin versus say this part of the skin, it would give the same response to this cell. So these just have bigger receptive fields, which makes them in some ways more sensitive, but their sort of spatial resolution is lower. And like I said, the reason for that partly has to do with the position of the receptor. So the Pacinian corpuscles are much deeper than the Meissner's corpuscles, for example. So any given amount of pressure on the skin is going to have a more localized effect on the Meissner's corpuscles than it would be on the Pacinian corpuscles. So it's just due to that depth difference that they have those different properties. Another thing that differentiates different receptive fields is their degree of adaptation. So we've talked about adaptation a little bit, but it's simply a property of a sensory cell, or really any neuron, to reduce it or change its response to a continuous stimulus. So in this case, what we're looking at here is the response or the axon firing of different types of receptors to a continuous stimulus. So some touch receptors have a rapid adaptation profile, some have a slow adaptation profile. So a Meissner's corpuscle, for example, is something that has rapid adaptation. And so you can see that here. So when the stimulus is put against the skin, the corpuscle or the axon that's attached to this corpuscle responds when the pressure is first applied. So this part of the graph is when the probe is first touching the skin, and during that time the axon is firing. But once the pressure remains constant, once you get to this phase where there's still pressure but it's not changing, that cell goes quiet, and then it actually starts responding again when you take the pressure away. Pacinian corpuscles also have rapid adaptation. They respond when pressure is first applied, and then they go quiet, and then they come back on when the pressure goes away. And then down here, Merkel's discs and Ruffini's ending are what we call slowly adapting. So they do respond the most when pressure is first applied, but then they keep responding at least at some baseline level during constant pressure. So that's kind of how the four different touch receptors in the skin are classified by the size of their receptive field. So Meissner's corpuscles and Merkel's discs have small receptive fields, whereas Pacinian corpuscles and Ruffini's endings have large receptive fields. And then the Meissner's corpuscles and Pacinian corpuscles have rapid adaptation. Merkel's disc, Ruffini's ending have slow adaptation. Again, and that's partly or mainly due to just the physical properties of those endings. So you can see here, Pacinian corpuscles and Ruffini's ending are both deep, and they both have large receptive fields, whereas the Merkel's disc and Meissner's corpuscles are more shallow, and so they have smaller receptive fields. And then the other thing is that the Meissner's corpuscles and Pacinian corpuscles are rapidly adapting, which again is simply due to the physical properties of those endings that wrap around them, which you can kind of see here. It's kind of explained here. So in a Pacinian corpuscle, this is what the little capsule that surrounds the ending of the axon looks like. Again, it's kind of like an onion. It's got layers of epithelial cells that have kind of some fluid in between them that allows them to slide past each other. So when you touch a probe against that capsule, the force from that probe initially gets transmitted through the layers where it presses against the axon, and that, again, that's what actually causes the change in membrane potential of that axon is when you push against the axon right here, that opens those mechanically gated channels, and that depolarizes the membrane. But then if you continue pressing within just a few milliseconds, the force, the pressure from that probe gets distributed around the capsule, and you end up with basically no pressure or no detected pressure on the axon. But then when you remove the probe, the capsule kind of returns back to its original shape, and that movement or that force gets applied to the receptor as well. And so that's why the receptor detects the initial force and the initial removal of the force, but it doesn't detect the force in between. And this kind of shows that it's the physical properties of that little capsule that causes this. Because here what they've done is they've removed that capsule. So this is something where they basically stripped that corpuscle off the nerve ending. So all that's left is the axon itself. And again, pressing on the axon directly does cause it to depolarize, but without the corpuscle, that depolarization remains. I mean, it does kind of drop off, but it's still there. as long as the force is applied, and then when the force is removed, the receptor potential returns to rest. So again, it's because of that corpuscle that the axon has different properties from other types of receptors. Now you might wonder, why would you even need axons that or touch receptors that have a rapidly adapting response? One reason, and you can kind of you've probably experienced this yourself, but if you have constant pressure against your skin, you kind of gradually become less and less aware of it. We all experience this every day. You know, when you get up in the morning, you put on your clothes, you put on your watch, if you wear jewelry, then over time, as the day goes by, maybe even within just a few minutes, you may start to forget or not notice the physical pressure from those things on your skin. So, you know, if you wear the same watch every day, or you wear the same jewelry every day, you may sometimes find yourself forgetting it's there, or suddenly worrying that it's not there because you can't feel it. And the reason you can't feel it is because those touch receptors in your skin have become adapted to that pressure. And so that's one of the reasons why we have receptors that adapt to those kinds of stimuli, because otherwise you would have to be sort of constantly aware of all the things that are touching your skin. Another reason that rapidly adapting receptors exist is because they're actually uniquely sensitive, especially the Meissner's corpuscles and Pacini corpuscles, those rapidly adapting cells. They are very attuned to vibration. So again, if this receptor really responds the most when you press down on it and then remove that pressure, then that sort of oscillating stimulus, so up and down kind of stimulus, is the optimal stimulus for this kind of receptor. But then you might wonder, why would you need receptors in your skin that detect vibration? In fact, here you can show for different types of receptors, they prefer different frequencies, in fact. So this Meissner's corpuscle, for example, what they're doing is showing the threshold amount of skin indentation necessary to activate that cell. So, and then at different frequencies. So here it's saying at 10 hertz, so about 10 times per second, if you press down on one of these receptors, then the minimum amount of pressure you need is about 100 microns of indentation. So pushing inward about 100 microns is all you need to activate this receptor if it's pushing in and out at a frequency of 10 hertz. And then at about 50 hertz, the threshold goes down. So somewhere, this is a log scale, so that's probably like 70 or so micrometers is how far you have to push to get a response at 50 hertz. So the threshold is lower. That means that it's more sensitive at 50 hertz. Pacini corpuscles, meanwhile, are even more sensitive, but you have to go up to a higher frequency. So at about 300 hertz, the threshold is all the way down here. So all the way at 1 micron. That's all you have to press inward for this particular receptor to activate it if it's moving in and out at 300 hertz. So again, why would that be? Why would you need vibration sensitive cells in your skin? Now, of course, we talked about vibration. We talked about the auditory system, and so that's one type of vibration that at least your auditory system is attuned to. But of course, you don't listen to things with your skin. Now, you might be able to feel a sound with your skin. So if you have a speaker or something and you put your hand against it, and it's playing music or playing a tone at those frequencies, you might feel some vibration through your skin. But of course, that's not the type of sensation that those receptors would be adapted to perceive. Instead, what they're really for is detecting texture. So you have to kind of imagine this. So let's say this is your finger. Hang on. So hang on. Okay, so let's say this is your finger. And there's the fingernail. My lovely artwork. And let's say that you are touching a surface like this, which is, has some sort of texture to it. And you drag your finger across it this way. So as you move your finger across this surface, it's going to be pressing against these little bumps and ridges that are part of this surface. And so that means that at each point, like here and here, you'll have touch receptors that are being activated at those points. But when you move this way, that finger is going to be touching those ridges as it goes along. And so that means that in the points in between those bumps, there will be the absence of pressure. In fact, the pressure against the skin will be sort of going up and down as you drag your finger along for any given point. And that's, again, the exact kind of stimulus that our touch receptors, or these rapidly adapting touch receptors in the skin, are able to detect. So that's one of the reasons why you need these rapidly adapting receptors, is to detect texture or to perceive texture. Now, another property of the receptors and their receptive fields, like we said, is the size of their receptive field. And different receptors have different sizes and shapes of receptive fields, and the number and type of receptors vary quite a bit across your skin. So again, your skin is your somatosensory receptor organ, but it's a big organ, and the sensitivity and distribution of these receptors can change quite a bit from one region to another. One of the ways you can measure the types of receptors in your skin at different areas is with this task called 2-point discrimination. And basically a 2-point discrimination test measures the minimum distance between two stimuli, 2 points, in order to be able to tell that they are separate stimuli. So this is done usually with this device here. It's called a caliper, and it's pretty simple. It's just 2 little points that are attached together at this hinge, and by turning this little dial, you can bring these points closer together or further apart. And the way that the 2-point discrimination test is done is your subject closes their eyes, or you do it at a part of the body they can't see, and you start with the 2 points close together, and you touch against the skin, and you just ask the subject if they felt 1 point or 2. And if they say 1, then you widen the points a little bit, and you touch again, and you ask them again, did you feel 1 or 2? And you do that over and over again until they say they feel 2 separate points. And that distance that your calipers are at is the 2-point discrimination threshold for that region of skin. And so what you can see here is that there's quite a bit of variation. So the skin along the back, for example, has 2-point discrimination that's 42 millimeters apart in some places. So that means that anything less than that, any 2 points that are closer together than 42 millimeters, you would only perceive as 1 point. Whereas if you look at places like the palms of the hands, the thumb, the index finger, the palmar surface of the fingers, the lips also, to some extent the toes, have much shorter 2-point discrimination distances. That means that this distance between these 2 points on the index finger, for example, is just a few millimeters apart in order for that part of the skin to discriminate. Again, the distance between these 2 points, the minimum distance, is dependent on the types of mechanoreceptors, their density, meaning how many of them you have per area in that skin, and the size of their receptive field. So presumably in the back, you have fewer mechanoreceptors that are spread apart more diffusely and have large receptive fields, whereas in the fingers, on the palms of the fingers, you would expect receptors with smaller receptive fields that are closer together. So that accounts for that difference. Now, why, you might wonder, would there be different degrees of 2-point discrimination at different points? And it reflects mostly the way we use these parts of the body. So the thumb and the index finger and the skin on the hand is used to feel surfaces. So we use those parts of the body as sensory receptors to detect objects and feel textures and to use tools and so on. Whereas the skin on the back, we just don't use that way. So you need to be able to feel pressure on the back, but you don't really need very high degree of discrimination on the back, because that, other than just feeling large amounts of pressure when you lean against a chair, for example, no one really uses their back to explore textures or shapes of objects. So we will stop there, and next time I'll talk about the primary afferent axons that go from the skin to the spinal cord.